In this video, we welcome you to enjoy the science of extreme with SERVO world-class lubricants. It is an undeniable fact that steel is the most important of all metals for its extensive use in almost all the industries. The rolling mill process is an essential technique used in the manufacturing of steel. Let us learn about the rolling mill process in this video. First, let us start with understanding the process of rolling. Primarily, the steel that is made from the iron ore by melting and heating with several other elements such as carbon, manganese, phosphorus, sulfur, etc. cannot be used as it is. This is because the steel attains the shape of the mold at the end of the process. In order to convert the steel and bring it to a desired shape by reducing the thickness or changing the cross-section, rolling is carried out. Rolling accounts for 90% of all metals produced by metalworking processes. These desired metal shapes include plates, foils, strips, and various sections such as bars, beams, rails, and pipes. Hence, rolling operation is the most vital metal forming process. Next, let's look into what rolling mills are. Rolling mills are machines designed to reduce the thickness of the metal to a specific dimension using a set of rolls and other components like screw, bearing, material, mill housing, etc. The process begins with the material being fed into the rolling mill. The rolls rotate the material and apply pressure to reduce the thickness of the material. The process of rolling can be repeated several times until the desired thickness is achieved. Depending on the type of material and the desired thickness, the rolls can be made from different materials such as steel, cast iron, or even a combination of different materials. These rolling machines can be classified into 2 high rolling mills, 3 high rolling mills, 4 high rolling mills, cluster rolling mills, multi-high rolling mills, and universal rolling mills based on the application and number of rollers used. The different types of rolling processes that lead to increased operational performance and production flow are discussed based on the different techniques like hot rolling and cold rolling. In hot rolling, the hot metal billet that is heated above recrystallization temperature is fed into the rollers. This way, the metal is compressed to the desired thickness. While rolling, the metal grains get elongated due to recrystallization and form deformed grains. In cold rolling, the metal billet that is below the recrystallization temperature is sent through a pair of backup rolls and work rolls. The billet passes through the work rolls. The backup rolls provide support to the work rolls by adding extra load. This prevents any bending or displacement in the work rolls during the process. Here, the metal grains get elongated, but they do not get deformed. However, irrespective of the hot or cold rolling, due to the amount of pressure and continuous rotation in the process, the rolling mills are susceptible to a huge amount of heat in both the rolls and the metal sheets. Hence, lubrication is the only solution to overcome this and ensure smooth operation of the rolling mills. Rolling mill involves bearing lubrication, grease lubrication, gear lubrication, hydraulic lubrication, and rolling oil coolant lubrication. Let's look at them one by one. First, let's look into bearing lubrication. This is the overall structure of the rolling mill with the lubrication system. It consists of the rolling mill with the bearings, lube tank, heat exchanger, and the cooling system. The lube oil from the tank passes to the heat exchanger and the cooling system and then enters the mill from where it makes its way to the bearings. This lubricant flow protects the bearings from being overheated. Bearing lubrication reduces the friction between the components and ensures prolonged bearing fatigue life. Once the lubricant spreads throughout the bearing, the heated lubricant flows back to the tank for recycling. Similar to the oil lubrication, grease lubrication is also applied to the bearings. This is a general representation of the grease lubrication system. The grease flows from the lubricant container through the air-operated barrel pump to the supply line. A controller is connected between the pump and the supply line. From the supply line, an injector injects the grease to the bearings. Grease lubrication is important to prevent bearing friction, corrosion, and contamination by dirt. Gear lubrication is equally important in rolling mills. The motors and gears are connected to the work rolls. Hence, they are equally exposed to continuous heat and friction. The lube oil from the tank flows from the cooling system to the mill and then through the motors and gears. Coating the gear with the lubricant and providing lubrication to the motor is vital, as it ensures surface wear protection, prevents corrosion of metal surfaces, and cools the internal parts of the gearbox. The next is hydraulic lubrication. Hydraulics play an important role in rolling mills, as they are responsible for easy rotation and movement of the rolls. Hydraulic cylinders function with the help of hydraulic piston rods that operate using controlled pressure. The roll movements are achieved with the help of the hydraulic lubricant oil in the hydraulic cylinders. Hydraulic lubrication has significant importance as it manipulates the roller movement, which in turn helps in achieving the desired metal shape and structure. Finally, let's look into rolling oil coolant lubrication. In the rolling mill process, the metal strip passes through a set of work rolls or a series of work rolls. Due to the continuous contact and the metal compression, the temperature of both the strip and rolls keep increasing, making it challenging to achieve a smooth finish in the metal. To make the two contact surfaces cool, oil and water emulsion is sprayed on the rolls and strip surface. This creates significant sliding speeds in the contact region, reducing the friction. Now, let's look into the range of Indian oil servo lubricants that are conditioned to different applications across the rolling mill process. For hydraulic lubrication, the lubricants used are servo system oils, servo system HLP oils, servo system XLP oils. For gear lubrication, the lubricants used are Servo Mesh SP, Servo Mesh XP, Servo Mesh Gold, Servo Syngear for bearing lubrication. The lubricants used are Servo Steel, Servo Steel EP, Servo Steel EP Plus. For greases, the lubricants used are Servo Gem EP, Servoplex LC. For water-resistant greases, the lubricants used are Servo Grease WR, Rex L1. Adding onto these, lubricants such as Servoplex PU1S or PU2 are used in the furnace charging area. Servogem Firex is used in the furnace discharge or pre-scaling area. Servogem EP2 or Servoplex LC2S is used in the ROT, and Servogrease WR is used in the mill and mandrel regions. And for hot or cold rolling mill oils, the lubricants are Servosterol H2, Servosterol H5. These Servosterol H2 and Servosterol H5 cater to several unique performance characteristics in hot strip mills, HSMs, which can be practically understood by exploring these case studies performed at the SAIL, Steel Authority of India Limited, Bokaro, and JSW, Steel Vijayanagar Works. First is the case studies conducted at the SAIL Bokaro HSM. The challenges faced during the hot rolling process of steel at Bokaro were high reduction requirement, high temperature and scale formation, high rolling force and power consumption, excessive wear and high roll consumption, frequent grinding requirement, more maintenance and cost. To overcome these challenges, the expectations from the lubricant were improvement in rolling surface property, reduction of roll wear and surface peel-off, reduction in power consumption, increase in production with high quality. Rolling mill at Bokaro also experienced problems of peeling off in the work roll surfaces due to the lack of roll bite lubrication RBL system. To overcome this challenge, Servosterol H2 was used in roll bite lubrication RBL system. This is the schematic representation of the RBL. RBL is introduced to ensure the desired increase in roll life, decrease in roll stock removal, increase in product quality, and increase in tonnage of product rolled. As a result of using the RBL system, the performance of Servosterol H2 proved to be extremely efficient. The campaign size increased by 20%. The specific roll consumption reduced by 20%. The roll force and power consumption decreased by 5 to 10%, and it also developed an ease in rolling of value-added steels in critical sizes. The next is the application of Servosterol H5 in edger roll lubrication ERL system. Vertical edger rolls are used in rolling mills to maintain the width of the slab and reduce the thickness by elongation. This is the schematic representation of the ERL system at Bokaro HSM. Each roughing stand is provided with a pair of edger rolls on both sides. On providing ERL using servo-steerol H5, it was observed that the campaign length increased by 23%. Roll force decreased by more than 5%. Specific roll consumption reduced by 22%. Power consumption decreased by more than 7%. And it also developed an ease in rolling of value-added steels in critical sizes. Overall, the use of RBL and ERL in the SAIL Bokaro HSM using servo-steerol H2 and servo-steerol H5 contributed to all of these factors. Increase in campaign length by more than 20 to 25%. Reduction in specific roll consumption by more than 20 to 25%. Decrease in roll force and power consumption by 5 to 10%. Ease in rolling of value-added steels in critical sizes. Monetizing these savings, SAIL BSL Bokaro is saving more than 10 crores per annum. Moving on to the case study at JSW Steel Vijayanagar Works. Servo-steerol H5 was used in RBL and ERL system trials in JSW Steel Vijayanagar Works HSM. This is the schematic representation of the process flow at JSW HSM. The trial was conducted to target aspects of oil flow, campaign length, and roll wear per campaign. During the trial, the performance parameters that were measured include oil flow rate, oil consumption per slab, oil consumption per ton, roll surface at the time of roll change, roll wear, stock removal. After the trial, these are the results observed on campaign length, oil consumption per slab, oil consumption per ton, roll stock removal, and roll consumption parameters in comparison with the existing oil and manufacturing operations management (MOM). From the overall comparison, it is evident that oil consumption reduced from an existing 80 ml per slab to 45 ml per slab, a decrease of 43.75%. Campaign length of 1 million tons achieved as against a target of 8 lakh tons, an increase of approximately 25%. Roll wear of 8.15 mm as against a target of 12 mm. An approximate 50% decrease in roll wear as compared to existing 17.5 mm roll wear. Additionally, the comprehensive benefits of using servo-steerol H5 in RBL and ERL are reduced roll stock wear, which in turn doubles the roll life. This results in roll cost saving up to approximately rupees 1 crore per annum, and roll change frequency is halved, saving approximately rupees 37.5 lakhs per month. Lubricant consumption halved, saving an approximate amount of rupees 2 lakhs per campaign. It also caters to several environmental benefits. Hence, using servo-steerol H2 and Servo Sterol H5 are practically proven to be the powerful and the most efficient lubricants in the rolling mill process. In conclusion, rolling mill is one of the most efficient and versatile processes in high-quality metal production. And Servo Sterol lubricants are the key to a damage-free, wear-free, and a less oil-consuming rolling mill process. Enjoy the science of extreme with Servo world-class lubricants. Thank you.